This is lesson 12, and it really isn't the integrals of inverse trig functions, but rather it's integrals with inverse trig functions, meaning we're going to be taking integrals where the answer is an inverse trig function. So we need to recall our formulas for the derivatives of some inverse trig functions. So the derivative of arcsine, and then seeing it in the chain rule format, and we have the derivative of arctan, and again in the chain rule format. So recall these two formulas. Like I said, we're going to concentrate mostly on arcsine and arctangent today. So now that you remember these formulas, I want you to do now in your notes two derivatives, and I want you to pause the video, and when you're finished doing these two derivatives, start the video again and then check your work. Okay. So hopefully you've done these. We are going to have to employ the chain rule, and so we have 1 over the square root of 1 minus the argument squared times the derivative of the argument, and the argument was x squared. And simplifying that, and then for the arctangent, we have 1 over 1 plus the argument squared times the derivative of the argument, and simplifying that, we have that one. So besides kind of reviewing and recalling derivatives of our inverse trig functions, we need to kind of get used to some ways to manipulate some different fractions and different radicals. So they're tricks, it's looking at them in different ways. So here is a square root of 4 minus x squared, which is a perfectly fine square root, but let's play with it a little bit. I'm going to look at that 4 and change that to 2 squared. I'm going to now factor the 2 squared out of those two terms. And since this is a perfect square in its multiplication, I can actually take this out of the square root, which is just a 2, and I'm left with the square root of 1 minus something squared. So I just kind of found a different way of writing this same radical. We're going to do it again with a different one, this time a fraction, 1 over a radical. And I'm going to employ the same method that I did here, where here I saw 4 was 2 squared. I see that 9 happens to be 3 squared. And I factor out the 3 squared from the terms. And then I realize that I can take the square root of 3 squared. Since this is multiplication, I can break this up and simplify it. And so I end up with 1/3 times that fraction of 1 over the square root of 1 minus x over 3 quantity squared. I want you to try to do one. It's going to look a little bit different, but think of the same format, the same way I was doing this side here. But here is a different one. I want you to do 1 over the square root of 7 minus x squared. So I want you to think about a way to play with that, pause this, and then start it up again to see how I did it. Well, the real trick is the fact that 7 is not a perfect square. Here we had 4 was a perfect square, and I could write it as 2 squared. But even though this isn't a perfect square, I can still think of something I would square to get 7. And the something I would square is the square root of 7. So I just wrote that as the square root of 7 quantity squared. So I still am writing it as a squared term. Factoring it out, and here now I've got x over the square root of 7, because I'm going to square that whole thing. So when you distribute this back in, we go back up to where it was. And I can then pull out 1 over the square root of 7. Now you might be saying, well, why? Why are we doing this? Why are we manipulating these radicals or these fractions? And that's because, one, we really love this format of 1 over the square root of 1, this 1 minus something squared, because this was the derivative of arcsine. And if that's the derivative of arcsine, then its integral is arcsine. And there was a pattern to what we were doing to this thing, and it was that I was able to write the first term as a perfect square and the second term under this radical as a perfect square. Then we would factor out that a squared, and we would end up with this. And so whenever I'm going to see something in this format, I can think that it would be written in this way. And if I was going to take the integral of this, it would be the same as taking the integral of its simplified. And now that I see this, I'm going to use u substitution, where u is x over a, and the derivative of u is 1 over a dx. So wherever I see 1 over a dx, I can write, and I have it here, 1 over a dx, I can write du. And so that simplifies to that integral, and this integral happens to be inverse of sine. Now I'm going to resubstitute back in for that u, and I end up with the arc sine of x over a plus c. And so this pattern here is what we found. It isn't that this is an absolute must to memorize formula. It's just that when you see something like this, this problem here, and you had to find the integral of it, you'd have to go through this whole process to find its antiderivative. But if we have it memorized, we can just go straight there. And this step here is not necessarily something you would be thinking of doing in the middle of a problem, and so it's best to just have it memorized then, that this is what it is. We're going to look at another pattern. This one doesn't have a square root, but it works out very similar, and that is that I can factor out this a squared. And when I do factor out the a squared, I'm left with 1 plus something squared. And I'm going to think of that one using u substitution for, and the fact is I have 1 over a squared dx. I only had 1 over a dx, so I multiplied both sides by 1 over a. And by doing that, I can now replace 1 over a squared dx with 1 over a du. And so I did. Here's the 1 over a du. So now I want the integral of this, which we know as arctangent. And I still have the 1 over a, the constant, out in front. And I'm going to resubstitute in for that u. And we now have this integral and its antiderivative. And again, it's another one that's good to memorize this pattern. It doesn't happen, often, but when it does, it's a very useful pattern to know. Please make sure you recognize both in this one and the one for arc sine that this x is a 1x squared. It does not have a coefficient other than 1. So we're going to do a couple of problems now. And these won't be the same exact pattern, but they will utilize it a little bit. So here is our first problem, and we see here that we have a 9x squared. So because of that, this is not just 1x squared. I'm not going to simply use the previous problem, the previous pattern that I was showing you. This one I'm going to take the constant 5 and pull it out in front. And then I notice that this 9x squared can be written as 3x quantity squared, which lends itself perfectly for u substitution. If I had a 3dx, I would replace it with du. I don't have a 3dx, so I'm going to take this du equals 3dx, multiply both sides by 1/3, and that way, wherever I see dx, I'm going to write 1/3 du. So I had the 1 dx, and so I wrote it as 1/3 du, 1/3 du, and I changed the 3x to u. I pulled out that 1/3 in front of the integral, the constant. That way I can see now, oh, here it is. This is arctan. The integral is equal to arctan, and I have the multiplied by the constant 5/3. Last bit is to resubstitute in for u, and we have that problem done. Next problem. Again, we don't have 1x squared, we have 4x squared, so we're going to pull out the constant of 3. We're going to write that the 4x squared as 2x quantity squared using u substitution. I don't have a 2dx, so I multiply both sides by 1/2. Now wherever I see dx, I replace it with 1/2 du. Pulling out the 1/2 so that I can have all my constants out in front. I can see that I have the inverse sine function with u, and I resubstitute back in what x, the 2x for the u. Warning, these two look very, very similar, but please look at the numerator. Here on the left it just is a 2, and on the right there's a 2x. They're very, very different. In fact, the integral of this one here is 2, because if you pulled the constant out in front, it's 2 times the inverse of tangent plus c. Over here, this one is a natural log. The antiderivative is a natural log. And why is that? Let's look at this by using u substitution. So I'm going to put 1 plus x squared as my u, take the derivative, I get 2x dx. And here is my 2x dx. So I just use substitution for all of that. That is the natural log of the absolute value of u. Substitute back in for the u, and we can see that that is the antiderivative for this integral. Now, over here, like I said, we just pulled the 2 out, and then we're left with what we know is the arctangent function. So, be very careful that the numerator, if it has a variable in it, don't be fooled into thinking that that is the pattern for arctan. I want you to try these 2 problems, do them in your notebook, pause the video while you're trying to do them, and when you're done working on them, you can work with your partners, work with your teammates, and get them done, and then you can start the video up again and I'll go show how to do them. So pause. Alright, well hopefully you have done them, and here's the first one. And I used my little trick before because this does not say 1 plus. So I need to make this a 1, and so what I do is I factor out that 4, or I write it as 2 squared so that I can write this whole term as a perfect square, because it really would have been 9x squared over 4, but 9x squared over 4 is 3x over 2 quantity squared. And I pulled this out just because I want to see this by itself, and now I'm going to use the u substitution. And unfortunately it says 3 halves dx. I don't have a 3 halves dx. I have this 1 over 4, but I'm going to do this in a different way where I'm going to see, okay, I've got 1/6 du equals 1 half squared, so I've got this 1/2 squared dx. And I'm going to show you again what I did is that I multiplied both sides of this, what it was 3 halves. I multiplied both sides 1 by 1/3. I did that first so that I could make that just 1 over 2. Then I multiplied it by 1/2 as well, so I had 1 over 2 squared. So now wherever I see 1 over 2 squared dx, I can write it as 1/6 du. So I have 1/6 du divided by 1 over u squared. Pull out the 1/6 in front. I can see that that's arctangent, and there's the answer. Problem B. Again, I need this denominator to be 1 minus something squared. So I'm going to go through the process of pulling out that kind of fancy way that we were able to manipulate these square roots, and the constants cancel each other out. I now use u substitution. I still have to use u substitution because I need this to be 1 minus one thing squared, not a whole mishmash of stuff. So u is root 2 over 2x. I take the derivative and I get root 2 over 2. Remember that root 2 over 2 is 1 over the square root of 2. So because I don't have that 1 over square root of 2 dx, I'm going to multiply this equation, both sides, by root 2. And you get wherever I see dx now, because now this is just dx, wherever I see dx, I'm going to replace it with root 2 dx. So there's my root 2 du. And pull it out, pull the constant out, and I can see that I'm left with arc sine. So I've got the root 2 arc sine of u plus c. Resubstituting back in, we've got the answer to the problem. That's the end of your lesson. Work on your homework, and I will talk to you on the next class day.